Hello, this is John, and I'm going to do a brief presentation on what is radiosity and how does radiosity work. It's actually just a friend was doing some investigation into the radiosity method, and I thought it's easy for me to perhaps just show everybody what I know about it. And I'm literally just doing this on the fly, but what I'm going to use as my sort of demonstration tools is I'm going to use two documents. The first ones that come into my head, but they're good documents. Daylighting calculations in practice. It is not relevant that it's daylight. It just so happens it is. It's from the Danish Building Research Institute. I think Velux. Did Velux? Yeah, Velux. Yeah, Velux. Well, supported by Cowie Fond. I don't know who they are. I know Velux did it. They do some nice supportive work in the industry. I like that company. Um, and yeah, and they just have this image, and it's a nice. They go through all the methods actually. It's a good document. You know, if you want to know about ray tracing, photon mapping, and radiosity, yeah, nice short. Which sometimes is what you want, isn't it? If you just want an awareness, you know, I don't want to be able to write a radiosity engine or anything like that. I just simply want to know what is radiosity. And here's a nice way to do it. The other one I'm going to use for a little bit more detail. What's that page? Is that really page 11? No, it's not. It's page 188. Right. Is the most excellent, completely outdated now. Wow. I mean, it's like very late 90s, I guess, early 2000s. Lightscape. Used to be by a company called Discrete, acquired by Autodesk. Ruined by Autodesk. Basically, Lightscape used to be the Radiosity engine for 3D Max, and then they kind of absorbed it into 3D Max. But in my opinion, it was not the same. I can remember where I used to work at the time, we did comparisons, like for like, proper apples for apples comparisons. It was not the same quality. Um, but anyway, this is the Lightscape user guide, right? And I mean, just read it. It goes into it's a real nice document. I haven't looked at this for a decade, but yeah, that's good enough. Yeah. Oh wow. Yeah, it's yeah, it's a real nice document. Okay. Right, so let's go. So, what is radiosity? Radiosity is the method of distributing light energy about a space. Now, what I mean by that is, if you have a well, imagine there's a window. It's actually got some blinds in it. That's not relevant. And the direct light is actually like where the blinds did not obstruct. So these patterns here. So the sun has put the light. Some of the blinds have obstructed, and the light has come in there. That is the direct light. Everything else is indirect light. It is bounce light. You know, the light hits the floor, then it like pings off. Some of the light goes off onto the ceiling, onto the walls, back onto that wall, yeah, and then it bounces back down onto the floor. And that is why. Imagine if there was no bounce light, this is what it would look like. Oh, where did that go? It was black a minute ago. There, go. Yeah. So do you see my point now? So the direct, if there was no bounce light whatsoever, the light would just sort of come in and sit on the floor. And think it's loads of like light energy is actually sitting there that has not been accounted for. That is not an accurate calculation, is it? So the light from the sun outside has come in and is stopped, when in actual fact there is significant more light that needs to be bounced around the space to give a more realistic rendering. Right? So radiosity is one of many methods. Alternatives are ray tracing, photon mapping. See, those are the only two I can think of off the top of my head. Um, of like I say, distributing the light energy about the space. Okay, so that is why we use radiosity. Now, radiosity was originally used for thermal heat transfer, and I think that was back in the 80s. That was where it started life, of transmitting thermal energy. And what is thermal energy? It is long wave energy. It is just basically the same thing as light energy, just outside of the visual spectrum, yeah, down into the infrared band. And we kind of just taken that to what we know as like the RGB values, the red, blue, green values. The bit that we do see, it um, well, traditionally it just bundled the whole lot together Yeah, and it just said, "Oh, I'm going to use that same principle to push around the space the light energy that we can see, not heat anymore, but uh, but visible light." And I think over the years, I noticed how like I know Dialux did it, I'm sure Relux does it as well, and AGI will do it, where you actually start to see color bleed. And I assume that's because it has now separated the color channels, and it is doing a radiosity count for the red channel, the green channel, the blue channel, and that's how you start to get color bleed. Back in the early days, the early 2000s, you'd have this like bright blue floor. So naturally, you should be seeing color bleed off the blue floor onto the ceiling. It never used to happen because there was no color transfer. But anyway, I digress. So, what actually happens with radiosity, right? So the way it works is actually this I like no let me no it's this is more accessible, right? So what you need to do is you always radiosity is quick. It is really quick, yeah. Relatively, yes, nice quick calc, and there are other advantages. In fact, have I even got Dialux on my machine? Dialux, no, no, don't worry about it. Right, okay. Well, so basically, what it does is, if you have a wall and a ceiling and a floor and a window, what it actually does is it will take the central point of the wall and just take the average of what light is coming and hitting that point there, right? How much light is landing on that point, and then it will times it by the surface area. So then it will say it will assume what fell onto that wall is this much light energy, right? So it's only done one, but all it did was look at that one point in the middle. Don't worry about all this gridding at the moment. Just assume that it's just a open wall, right? So it looks at that point and says, okay, let's we could say like okay, 100 lux, or yeah, 100 lux fell onto that point, and I have this much wall, so I know there is X light energy on that wall based on those assumptions. And then let's say the wall has a 50% transmission value, 50% reflectance, and what that means is the wall will sort of absorb and retransmit as heat energy, stuff we can't see. So as far as lighting is concerned, it's gone. Is 50% of the light. 50% of the light that fell onto that wall will be absorbed. The other 50% will be retransmitted. And it will do the same thing for this wall and the ceiling and the other spaces. Now, going back to my original point of saying it just puts one, let's say we just put one point there and make an assumption for the entire wall. The issue with that is it is massively inaccurate, isn't it? Because the light, it is not, we can see even in this image, it is not the same brightness across the wall. So then what it starts to do is say, well, that's not realistic, is it? So it can be a user input, or not, but it will start to divide up the wall space, and that's what's happened here. So imagine if you divide the wall into a mesh, yeah, like two meshes. So there's that bit and that bit. It'll say, let me choose the center of that mesh. Now, what is happening here? And I'll average it for that space and what is happening there, and it's a bit more accurate, isn't it? And then it will go a step further, in if it's depending on how the calculation is set up, and it will say, well, I'm going to divide it even smaller into four parts, yeah. And then it's like, what is happening? And we're getting more accurate, and that's what's happened here. And it's divided it, and it's divided it, and it's divided it. And now it's saying what light is falling onto the center of that mesh piece there, and then I will times it by the area, and I will say, I will make the assumption that whatever fell here is the same as what fell here and here and here and here and here. So I know in that triangle of wall there is X light energy. And it does that across the full space. So it sort of hoovers up all the light energy that fell on the space. So imagine this is like the fast bounce of light. So what we now have is a wall with lots of light energy trapped into it. And as we've said, let's assume all surfaces are 50% reflectance. Okay. So what that means is that 50% of the light that fell on that surface will be reflected as light energy. The other 50% will get retransmitted as heat. We won't see it. So so then what it was so then what actually happens is every single one of these triangles effectively become light sources. And it says, I now say, this is a light source with, I don't know, let's just say like 10 lumens of energy. Actually, let's make it a bit more beefy than that. Let's say 100 lumens of actually, that would be a lot, wouldn't it? 10 lumens of energy. Okay, in that square there, and 10 lumens in that one. And okay, this is more in the shadow, isn't it? Let's say there's only 5 here. So they're all light sources. So then what it does is then rebroadcast that light energy back into the space. And then it says how much light from this point got to there, got to there, got to there, got to there, and so forth. So every single one is a light source, and every single one is also a collector of light energy. So then it will total it up, and so let's say it says, okay, I am interested in how much light this one receives. So it will say what light came from here to there, what light came from there to there, and so forth. It's thinking of them all as little triangular luminaires. It's a real fast calc, the direct, because it's just a direct A to B calc. That's very, very fast indeed. It will factor in obstructions, of course. Right, so once it does that, and it's done one pass, and then it loads in that energy. So it's dissipated that first lot of energy. That's all gone now. And there's a brightness to it. And then it kind of says, okay, so I collected all that energy. Then it does the next bounce of light, and it says, so it's done it for every single triangle here. Then it says, right, next bounce of light. So now it's got that much energy in it, so it passes all the light to all the other triangles in exactly the same way. And then there's a transfer in the opposite direction, and it's summing up all the light that keeps falling onto it, and it's building up the luminosity of every single triangle. So I hope that makes sense. But perhaps like if you read through that, and in conjunction with what I've said, it will start to make sense. But the important point is that the denser the mesh, it actually, and this is where the lightscape stuff comes in. So here's an evaluation of like what it's saying is, imagine if you've shined, I haven't read this yet, but I assume it's saying, imagine if you shone this circular spotlight onto this wall and it meshed it off like that. So it's done it into 12 meshes. Yeah, and it said what's happening here, what's happening there, and in the center, and in the center, in the center, in the center. What you get is yeah, there's a nice example. Yeah, you start to get something like that, because what's happened is it took the average of a point, yeah, and whilst it was trying to do a circle, you've actually started to get this blocking. They used to call it artifacts, I think, and you start to get these coarse, yeah. So you start, and then basically it does a blend between each mesh. So when it looks at each point, it says, well, this one's got like this was like 10 lux, that was 20 lux. So it blends between the two, and it never used to quite work properly. They've got a lot more sophisticated in the past 10, 15 years. But you start to get that, you're trying to achieve that, and you got that. So when it starts to use a more coarser mesh, it starts to look a lot better. Okay. So basically, the point I'm making here is that the more you divide up the space, the more accurate the calculation becomes, but the more time intensive it becomes. Because let's say originally, let's say we just had 12 light sources to do that calculation. They collect the light, and then they become light sources and fire them back out into the space. 12, that's nothing at all. Look at how many are in that one there. Yeah, so the calculations got slow. It's still really quick, but just be aware, it becomes slower, and it just keeps totaling up slower and slower and slower. So in a coarse example, you just sort of, regardless, just say, look, just divide absolutely everything into 12, or it could be into 100 pieces. Doesn't just divide it all like that, exactly the same. And then as time went on, you started to get what was called adaptive meshing. That's a word I'm sure it was called adaptive meshing. And what it was is it would do a first pass, and then it would look at the direct light that fell onto it, and it would say, nothing's really changing here, so I don't need a dense mesh, but there's a very, very big change from here to here, so I'm going to make a more dense mesh there. I think Lightscape used to do it very well, and I remember 3D Viz and that, it made such a hash of it. It used to take, the idea is it's quicker, look, so you're not wasting time like you do a very big, because when on the original calc, nothing much changed. It says, don't worry about it, just check there, and it's going to be all right everywhere else. And then it gets tighter as you go in, because it starts changing more quickly. And the idea was that you would, it would happen, and this, I think that I'm sure this is how Dialux and Relux do it. Because you don't actually get to control, like, you as the user. I think there used to be a setting of like coarse calculation and fine calculation, and what it's actually doing is controlling the meshing tolerance. So if you said, "Oh, do me a coarse calc," it would never do it like that coarse, but you're sort of saying, "Oh, just do the calc like that, and it'll be really quick." And if you said, "Do me like a fine calc," oh look, that's a nice example, isn't it? From not that to that. Um, Yeah, you want to read this chapter. It's going to be really useful. What is it? Page 194. So imagine that would be like your course, and that would be your fine calc. So the detail would be superior, and the render quality would be superior. So it divides it all up, and then it can look at this, like look at the changes in illumination in luminance on the direct calc, and adapt the mesh accordingly. So hopefully that's, oh, and then so then it keeps bouncing the light around. It's going to keep bouncing the light around. So you remember how I said, so it looks at this square here and it says, right, let's say on the direct calc, what light gets to this point from direct? So it's just straight. Hang on, why don't I just use the ones they're highlighting? So from the window to here, right, so it's got this much energy from the window in that patch. So all the light from the sun has been collected. So forget about the sun. That's got nothing left to give. Now, there's for every single square, there'll be a quantity of light loaded into it. So it says, right, that's now a light source, and it passes it over, and it fires it all back out into the space. And then it fires it out, and they fire it back. It collects up all that light. Now you're on the second bounce, and it repeats it. But remember, a quantity of the light was lost in the transfer because we've only got 50% transmittance, 50% reflectance. So only 50% is less, and it repeats the bounce again. And it lost another 50%, and then it repeats the calc again, and it's going to got another 50%, and it will keep going until you get to the point where you're like, in theory, it will go to infinity, of course. You just reduce 50%, run it again, reduce 50%, run it again. And what it will do is there will be a tolerance built into the calculation engine, and I don't know what they are, but and it will say, look, when this is how much light started. Remember, the sun had this much light inside it, or actually, I'm saying the sun. There's a light bulb there, isn't there? All right, so the light bulb had this much energy in it. Let's say there's like 1,000 lumens of energy in the light bulb, and when I look around this space, I can now account for like 90, I don't know, 95, 97% of that light energy. It's time to stop, because I'll repeat the calc again, and the accuracy will only increase by 0.1%. There's no point. The time will be the same. It's always the same time, but the results become less and less significant. So the tolerances just keep transferring the light energy between yourselves, and when we've accounted for like 95% of light energy, just call it a day, and that is accurate enough. Right, that's how it works. So what are the limitations of using the radiosity method? And there's a real big one that can become an issue. And so, well, firstly, there's obviously the accuracy issue that if you're using too coarse a grid, you will start to get artifacts, and you may start to get inaccuracies. So you need to understand, what is the accuracy requirement of the calc. The other one is did you remember how I said it was actually born in thermal energy transfer? And what that means is it assumes no matter some surfaces are glossy. Think of a bit of polished metal versus a carpet. Yeah, one is like a rough material, one is a specular, and they will have different, when the light hits it from different angles, it will have different effects. What radiosity does is it actually simplifies it by saying that all surfaces have a light redistribution, what's called a Lambert distribution, which is a, if I go light Lambert, yeah, and basically what it assumes is when light, doesn't matter whether it's a piece of metal or a carpet or a matte finish wall or a polished reflector, a mirror, um, they're all exactly the same. And when light, imagine if you had a bit of like polished metal, right? Your light is going to come in and it's going to bounce off at that direction, isn't it? And you get that kind of, that's how you get those sort of veiling reflections, those highlight reflections. In a radiosity calc, it assumes the light comes down and gets evenly scattered, totally evenly. What goes in that direction is the same in that direction. If you don't know polar curves or anything, don't worry about that image. Just trust me that it comes in and it gets evenly scattered about the space. So you start. So imagine if you had a room that was full of shiny tiles or some ceramic tiles, something like that. You actually start to get you may start to get an inaccuracy because the radiosity engine is assuming that all your specular surfaces are just dull, flat, matte surfaces. Generally, it's fine because you're going to have a room, you're going to have some floor tiles, you're going to have a matte finish and ceiling tiles. So everything's diffuse anyway. But just be aware that if you were doing it like an environment full of lots of like maybe it was a kitchen full of lots of stainless steel and stuff like that, it's possible you could get an inaccuracy. But most of the time, it's all right. So that's the second limitation of the radiosity engine. It also it can't do because of this phenomenon where it equally scatters everything. If you had a mirror, it wouldn't be able to render the image in the mirror. And that makes sense if you think about it, because a mirror is specular reflections. The light hits the mirror and bounces off. Like it's like like a laser beam of light. If you shone it at a mirror, your laser beam would bounce back off again, and you would see it, wouldn't you, behind you? But if you got your laser beam and you shone it just at a matte finish wall, you would not see that beam bounce off the wall behind you. It would get evenly scattered. And it's for that phenomenon, that assumption in the calculation is why you can't see through glazing or anything like that. Because actually, I think in later versions of the radiosity engine, they got around it. It's beyond the scope of what I can be bothered talking about. But it used to be that, if you have glass, it can only take the reflective portion of the glass, which is very low, like 5%. And basically, it would just assume that transmitted portion of light is just lost. So limitations of radiosity, you can't transmit light. You can't transmit light, so it will not accurately render a sheet of glass. Secondly, you can't do like mirror reflections in it. You'll lose all that data. Thirdly, all materials are assumed to be matte finish, perfect diffusing materials. And finally, there's the phenomena of it simplifies. It's like it's not sampling every single point. No method of light calculation samples every single point. It makes this assumption, and inaccuracies may sneak in. Just so I don't confuse. I said about how actually let's that this calc isn't actually doing daylight. No, it is actually, isn't it? The way that I think the way they got around it with glazing is what they actually did was say it like on one, it does actually two calcs. Is on one side it collects all the light on each triangle, and then rather than reflects it on the other side, like on the flip side of the window, it just turns it into a light source, if that makes sense. So the light, rather than just bouncing the light back off, it actually looks on the other side of that surface and says it is now a light source. But the same phenomenon happens. It's if you had a very direct light source coming down, it will say, well, the light coming through is perfectly diffuse, as though your window is translucent, as far as the radiosity engine is concerned. So that's limitation. So the positives are it is very quick. It will. One of the limitations of the ray tracing method is you have to define. Ray tracing is a different method of light distribution. You have to define the ray bounces, and And if you get it wrong, if you say, oh, there was only four light bounces or three light bounces, even if you said, well, I've only used up 50% of the light energy in your scene, so this is an inaccurate calc, it will just stop because you said stop. The radiosity method, it will keep bouncing the light about until it said, right, I've now used up. I know now that I have adequately distributed 95% of the light energy in the space. So that's a good one for radiosity. And finally, if I had a copy of Dialux on this machine, I could have or Relux, I could have shown you what you find in when you do a ray trace calc. At the end of it, you get an image, just one image, and it was where you happen to be pointing your camera. So if your camera was here, you're stuck with that static image. And the reason is because it was the rays of light specific to that view. That's what it always does. Radiosity is view independent. So what you'll find in your engines, when you've done your radiosity calc, is you can look at it in 3D and move around it. And you get it. It's certainly not as good as a ray traced image, but it's not bad. You can generally understand how the light is behaving in the space. You are free to sort of spin around and explore that space with the radiosity solution baked onto the image. It is not view dependent. So that is a strong positivity for radiosity. Okay, so that's radiosity calcs for you. Maybe at some point I'll go through ray tracing as well. It's a bit more complicated. And a bit more interesting. But yeah, hope that's useful. And yeah, no. Oh, and just one thing to labour is you don't have to, you don't, when you're doing your calcs, you don't have to tell it how much light energy to dissipate. It's already built into the software. And generally, when it comes to carving up all these settings, the only one the only setting you ever have to do usually is say, do I want a coarse render or a fine render? And it's usually set to the medium setting. So it's all taken care of it all for you. So it's another positive with ray tracing, with radiosity. Right. Thank you for listening, and yeah, take a look at that. I strongly recommend all those documents, particularly Lightscape, but it's just making me go all nostalgic for the good old days. Yeah, look at that, 1999. Okay, take a look. Bye bye.